Now let's work a more complex proof using only the inference rules that we have among our axioms. So let's start with an overall look at this proof. So we have four premises, P and not R. Second premise, not S or P implies T. Third premise, T implies Q. The fourth premise, Q implies R. The conclusion that we want to derive is this rather complex expression, T or, not T and not R, and T implies R. So let's start with some thoughts about this conclusion, and as I mentioned before, a good rule of thumb is to sort of try to work backward and see where you could derive the bits and pieces that we want to construct the conclusion. So if you look at this conclusion, you'll see its major operator is conjunction. So that means that if we had the two sides of the conjunction, we'd be able to combine it together as the final step of the proof to derive this overall. So what do those two components look like? Well, on one side we want T implies R, and on the other side we want this complex expression T or not T and not R. So let's start with this side. Is it plausible that we could derive T implies R? And actually, if you look at lines 3 and 4, you will see that it's a fairly straightforward case of hypothetical syllogism that would allow us to derive this part. So this part is going to be no problem. And so our conclusion by hypothetical syllogism is T implies R. So this part is not too difficult. This other part is going to pose a bit of a challenge because what we need is to see where we could get the components of this. So let's look again. We always want to start by noticing the major operator. The major operator is disjunction. And so what are some rules, some inference rules that allow us to work with disjunctions? So one that came to mind for me looking at this was addition. Remember, if we have addition, if we invoke addition, we will have either one side or the other. So if we had one side or the other standing alone, by addition, we could add the other part to it. So looking at this proof, it makes you wonder, okay, so where could we get either T or the expression not T and not R? So one of the things that I noticed in the premises is that we already have not R in the first premise. So if you look here in the first premise, we have not R. It's very easy to derive by simplification. So we could at least get the not R part. Where, if anywhere, could we get the not T part? If we could get not R from line 1 by simplification, and we had not T, then we could essentially build this side, the triangle side, by the inference rule conjunction, and then just use disjunction to add T onto it. So that looks pretty promising as a line of investigation. So our question is, we have not R without any problem. Let's see if we can find a way to get not T. And here's an interesting thing. Since we know from this step here that we can get T implies R, and we know from this step that we can get not R, then it turns out we can pretty easily derive not T if we do this hypothetical syllogism first and then use not R to do modus tollens. So if we apply modus tollens to that piece, which we'll have to derive anyway by hypothetical syllogism, and we take advantage of the not R that we just got here, we'll have this part that we need. We can build this side, not T and not R, by conjunction, and then we can just take this and use addition to put t on the front end. So that'll be our addition step. So looks like this proof is now pretty much solved. What we'll need to do in terms of our strategy is we'll need to derive the T implies R by hypothetical syllogism first. Then we'll derive not R, and we'll use this to derive not T. We'll join those together with conjunction, and then we'll add with disjunction, and then we'll have this piece and this piece, and we'll join those together by conjunction, and that'll be the very last step of our proof. So let me get rid of all of this and go back to our proof, and let's put this proof together. So on line 5, we'll start by deriving T implies R by hypothetical syllogism applied to lines 3 and 4. So notice we're following the schema of hypothetical syllogism. On line 6, we will derive not R from line 1 by simplification. And once we have that, we can derive not T by modus tollens applied to lines 5 and 6. And as we saw in our the working backward phase, you may want to scroll back a bit and look at the notes we made. What we'll do now is we'll combine not T with not R using conjunction. So that's going to be conjunction on lines 7 and 6. And then on line 9, we will use this unit as the basis for addition to derive T or not T and not R, just like that. That will be addition on line 8. Notice that addition has only one premise in its schema, so we have only one line number that corresponds to that premise. And then on line 10, we'll take the result that we just got on line 9 and the result that we derived earlier on line 5 and combine those together using conjunction to derive our conclusion. Not T and not R, that's that part, and now from line 5 we have T implies R, so that will be conjunction on lines 9 and 5, and notice I'm putting them in this order because of the schema. And now that we've derived this complex expression that we were aiming for in the conclusion, we can say that this proof concludes. So this is a little bit more complex example of a proof that we have been able to construct using only the inference rules in our set of axioms.